Welcome, viewers, to the sixth and the last segment of the seventh lecture for the online series of lectures for the course of differential geometry. Towards the end of the last segment, we discussed how we can find the orthogonal group as a regular submanifold of the general linear group. In this segment, we are going to discuss immersion and submersion theorems and various examples related to those two theorems. The immersion and submersion theorems. Consider a C-infinity map F from the manifold N to the manifold M. Let U comma phi is equal to U comma x1, x2 all the way up to xn be a chart about P in N and V comma psi in terms of local coordinates which reads V comma y1 y2 all the way up to ym be a chart about f of p in the target manifold M. Also write f small f I equal to yi composed with the C-infinity map F. These are the M components where I runs from 1 to all the way up to M components of the smooth map F i's relative to the charts U comma phi and V comma psi, that is in terms of basis, the basis del by del xi at P where I runs from 1 to n. This is the basis of the tangent space TPN, and the basis del y j at f of P where j runs from 1 to m. This is the basis of the tangent space TFPM. So with respect to these two bases, the linear map F star comma P, which is the differential of F at P. This is a map between the tangent space TPN and TFPM. This linear map is, with respect to those two bases, this linear map is represented by its Jacobian matrix, by the matrix del Fi by del Xj at P, okay, where I runs from 1 to M and J runs from 1 to N. This is an M times N matrix, and this is so by means of proposition 4 of lecture 6. Okay, hence F star comma P, this linear map here, is injective This statement is equivalent to the fact that n is less than or equal to m. Okay, we know it from our previous discussions. And the rank of this Jacobian matrix del fi by del xj at p is equal to n. Why is it so? It follows from the rank nullity theorem. Since this is injective, the kernel is trivial. In other words, the nullity of this matrix has to be zero. And hence the rank of this matrix has to be n, which is the dimension of this domain tangent space. Okay. Also, f star comma p is going to be surjective, is equivalent to the fact that m is less than or equal to n. So instead of n is less than or equal to m for the case of injective, it's going to be m is less than or equal to n, which also follows from our previous discussion. And in this case, the rank of the Jacobian matrix at p is equal to m, right? So together, this and this, we number these two equations by 20. Okay. Now, the rank of a matrix is the number of linearly independent rows or columns. Linearly independent rows or columns, right, of that matrix. Since the matrix, this Jacobian matrix del fi by del xj at p is of size m times n, I varies from 1 to m and j varies between 1 and n, and hence the size of this matrix is m times n. And since the size of this matrix is m times n, and the rank of this matrix del fi by del xj at p is less than or equal to minimum of these two numbers, m and n. Okay, minimum of these two positive integers, m and n. Therefore, from the equation 20, which describes the two cases in detail, when f star comma p is injective or f star comma p is surjective. Okay, from that equation 20, one finds that whenever f from n to m is an immersion or submersion at p, remember, when f is an immersion at p, f star comma p is injective, and when f from n to m is a submersion at p, f star comma p is surjective Okay, so whenever this map is an immersion or a submersion at P, the matrix del Fi by del Xj at P is of maximal rank. That is, its rank is either n or m respectively. Okay, good. Okay, now the point is that having maximal rank at a point is an open condition in the following sense. Is an open condition in the following sense. The set D max F, we are going to define this set as the points in the open set U such that F star comma P has maximal rank at P. Okay, so it's the collection of all the points P in the open set U such that F star comma P is of F star comma P has maximal rank at that point P. Okay. So having maximal rank at a point is an open condition in the sense that D set D max F is an open subset of U. D max F is an open subset of U. How do we see this? Suppose K is the maximal rank of this smooth map F. Okay, then rank of this linear map F star comma P is equal to K. This statement is equivalent to the fact that the rank of the pertaining Jacobian matrix delta Fi over delta Xj at P is equal to K, right? And which is equivalent to the fact that it's immediate that the rank of this Jacobian matrix is greater than or equal to K. Okay, so let me explain this equivalence a little in detail. The last implication from the left to the right is obvious, and okay, which means that rank of this matrix is equal to K implies rank of this matrix is greater than or equal to K, since equality holds greater than or equal to trivially holds. Okay, and the last implication from the right to the left holds, that is rank of delta fi over delta xj at p is greater than or equal to k, implies rank of delta fi by delta xj at p is equal to k, since k is the maximal value of this rank. Okay. All right. Now let us try to see why that set D max F is an open subset of U. Okay, so what do we want to show? This is the open set U, and here inside which is D max F, okay, which is the collection of all the points of U such that F star comma P is of maximal rank. Okay. So from the above discussion, we see that the complement U set minus D max F is defined by the rank to be the rank of the Jacobian matrix to be strictly less than K. Okay, this is our equation number 21, which means that the determinants of all K times K submatrix of this Jacobian matrix del Fi by del Xj at P will be 0. This is because in such a submatrix, not all the rows or columns will be linearly independent. Why? Because the rank is strictly less than K. The rank of the Jacobian matrix is strictly less than K. Okay? Good. Now, use the fact that the zero set of finitely many continuous functions is closed. Okay, so let me elaborate on that. Suppose f1, f2, all the way up to fn be n functions from a topological space X to the set of real numbers, and we want each of these functions to be continuous. So these are continuous. Then the inverse image of each of these, inverse image of the zero here under each of these continuous functions is closed in X. Follows from the continuity of each of these functions is closed in X for each I. Then the zero set of f1, f2 all the way up to fn is the common zero set of all these n functions, is equal to the intersection of all these sets, and this is closed in X. Okay, good. So using this argument, we see that the zero set of finitely many continuous functions is closed. Okay, so let me erase. And so U set minus D max F is the collection of all P in U on which all the determinant functions on K times K submatrix of this Jacobian matrix del Fi by del Xj at P vanish simultaneously, right? So we are looking at the common zero set of the determinant functions. Determinant functions on all K times K submatrices of this Jacobian matrix del Fi by del Xj at P. So from which it follows that U set minus D max F is closed in EU, that is D max F is open in the set U. In particular, if F has maximal rank at P, it has maximal rank at all points in some neighborhood of P. Okay, whenever it has a maximal rank at a point, it's not at just that point on which it's maximal. It's automatically in a neighborhood of that point where the rank is maximal, which is denoted by D max F here. Okay. Now we summarize all these results formally by a proposition here, which will be proposition 2. Proposition 2, let n and m be manifolds of dimensions n and m respectively if a C-infinity map F from n to m is an immersion at a point P in the domain manifold n, then it has a constant rank n, okay, in a neighborhood of P, in a neighborhood of P. We have seen that if it is an immersion, then it has maximal rank, and since it has a maximal rank which is equal to n in this case at a given point P, then it has to be of maximal rank in a neighborhood of that point P. Okay, so it has a constant rank n in a neighborhood of P, and in this case m is greater than or equal to n. Now if a C-infinity map F from n to m is a submersion at P in n, in which case n is greater than or equal to m, then it has constant rank m in a neighborhood of P. Okay, good. This is a very important proposition that we are going to use to prove immersion and submersion theorems. So now it's time to give you and provide an example. Although a maximal rank at a point implies constant rank in a neighborhood that we have seen a while ago, the converse of this statement is not true in general. The converse is not true. Suppose the map F from R2 to R3 is defined by f of x comma y is equal to x comma 0 comma 0. This has Jacobian matrix del x comma 0 comma 0 del over del x comma y. Okay, so we are going to take the first component and then derive it with respect to x and y. So we have the first entry to be 1, the second entry is 0. So here, so the second component is 0, so everything is 0 here, and the third component is 0 as well. So this is the Jacobian matrix. These matrix has constant rank 1. So the rank of this matrix is 1. Okay, this matrix has constant rank 1 everywhere in R2. Okay. On all of R2, these matrix has constant rank. The rank is 1, right? This rank is not maximal, right? That is, the rank of this Jacobian matrix delta x 0 0 over delta x y is not equal to 2, which is the minimum of these two numbers. The size is 3 times 2, so the minimum of 2 and 3 is 2, and the rank of this matrix is 1. So it is not maximal. So although this rank is constant, it is not maximal. Okay, now it's time to state these two important theorems, immersion theorem and submersion theorem. So it's immediate that proposition 2 that we proved in this last segment plus constant rank theorem for manifolds, which is theorem 3, theorem for manifolds, imply theorem 5, let n and m be manifolds of dimension n and m respectively, okay. 1, which is the immersion theorem, suppose f from n to m is an immersion, okay, which means that n is less than or equal to m, follows from the previous discussions. Suppose this immersion this is an immersion at P in N. Then there are charts U comma phi centered at P in N, and V comma psi centered at f of P in M, such that in a neighborhood of phi of P okay, since the chart U comma phi is centered at P, we know that phi of P is equal to the zero vector in the n-dimensional Euclidean space. Okay, so such that in a neighborhood of phi of P, one has psi composed with f composed with phi inverse at R1, R2 all the way up to Rn is equal to, so on the right hand side I should have an M tuple, right? And this is R1, R2 all the way up to Rn, and the rest are 0. They are all zeros. So how many zeros are there? M minus n zeros. Okay, remember n is less than or equal to m. Okay, so now the submersion theorem. Suppose f from n to m is a submersion at P in n. In this case, n is greater than or equal to m. Then there are charts U comma phi centered at P in n, and V comma psi centered at f of P in M, such that in a neighborhood of phi of P, and again phi of P is equal to the zero vector in R to the n, one has psi composed with f composed with phi inverse at R1, R2. Remember, n is greater than or equal to m in this case. Okay, so R1, R2 all the way up to Rm, after which comes Rm plus 1, and all the way up to Rn. Okay, and this map looks locally like a projection. So I'll just have an M tuple on the right hand side, R1, R2 all the way up to Rm. This is equation number 22. So a very important corollary to this theorem 5, the immersion and the submersion theorems. Now I'll state that corollary. and prove it. Corollary to theorem 5. A submersion F from the manifold M to the manifold M is an open map. Okay. In other words, F maps open sets of N to open sets of M. Here goes the proof. Let W contained in N be open and P be a point in W, so that F of P is in F of W. Okay. Now, F from N to M is a submersion at P by hypothesis, right? It's a submersion at any point on N, since it's just a submersion. So it's a submersion at P by hypothesis. Then by submersion theorem 2, okay, provided under theorem 5, under theorem 5, there are charts U comma phi centered at P in W, and of course W is contained in N, and V comma psi centered at F of P in F of W, and F of W is contained in M in the target manifold, such that in a neighborhood of this point F of phi of P, which is the zero vector in the m-dimensional Euclidean space, one has psi composed with F composed with phi inverse at R1, R2, all the way up to Rm, Rm plus 1, all the way up to Rn, is just the first M tuple, R1, R2, all the way up to Rm, because it is locally a projection, right? So let me draw a figure at this stage. We have W here is an open set in the domain manifold, and this is our open set U. Okay. And this is the point P. in W. Okay, so this open set U, this is the open set that exists by submersion theorem. Okay, good. Now, okay, we can take U small enough so that U is contained in W, right? We can take a smaller U here, okay, this U. So let me write it here. These open set also works in submersion theorem so that U is contained in W. Okay. Good. Now consider the subset. The subset f of W contained in M. Okay. Any point in f of W is of the form f of P with P in W, right? But from the previous argument, it follows that for P in W contained in N with W open, one can find an open set U contained in W with respect to which F acts as a local projection. Okay. As a projection is an open map, I want you to prove it. As a projection is an open map, prove it. F of U is open in the target manifold M. Hence, for every f of p in f of w, one can find f of u open in M such that f of p is in f of u contained in f of w, right? This is because u is contained in w implies f of u is contained in f of w. Okay, this proves that f of w is open in the target manifold M, QED. Okay, good. Now we'll end this lecture with an example. Example of image of a smooth map. So we are going to focus on this function. F of t is given by t squared t to the 3. Okay, observe that for this function f of t1 is equal to f of t is equivalent to the fact that t1 squared t1 cubed is equal to t2 squared comma t2 cubed. Okay, and this implies that t1 is equal to t2. Okay, so let me comment on this function. The equality here for the second component t1 cubed is equal to t2 cubed forces t1 is equal to t2, although t1 square is equal to t2 square has two solutions. t1 is equal to plus minus t2, right? That is the one-to-oneness of this function of the function f of t is due to the one-to-oneness of the second component. Okay, these function f from r to r squared is represented by a capital cubic. And the capital cubic is drawn in this way, 1 minus 1, something like this. Okay, all right. Now for this cuspidal cubic, f prime at 0, the velocity vector, sorry, it's not the velocity vector, so yeah, f prime of 0 is just the differential of f at 0 acting on this it's the velocity curve, is the velocity vector of the curve f, right? F is a curve. So the velocity vector for the curve f at the initial time 0 is the differential f star comma 0 acting on the tangent vector d dt at 0. And that is supposed to be a tangent vector in the tangent space t0 comma 0 r2, right? So which we write as a linear combination of the basis vectors del x at 0 comma 0 and del y at 0 comma 0. Okay, and this implies that d dt at t equal to 0 acting on x composed with f, right? So so by acting both sides of this equation on x, we'll have a on the right hand side only, and that means so the x component of the curve f is just t square. It implies d dt 0 t square is equal to a, which means a is equal to 0. Similarly, one obtains b is equal to 0, hence the velocity vector at time t equal to 0 is just this matrix, 0 matrix, so that the differential f star comma 0 as a linear map between the tangent space t0r and t0 comma 0 r2 the differential f star comma 0 of the 1-to-1 map f from R to R2 given by f of t equal to t squared comma t cubed is the zero map, which means that all of t0r, every vector in this tangent space, is mapped to the 0 comma 0 in the tangent, the 0 comma 0, the origin of the tangent space 0 0 t00 r2 under the differential. Okay, and hence this map f star comma 0 is not injective. Therefore, F is not an immersion at 0. Okay, so this example tells us that a one-to-one map is not necessarily an immersion. Although the map F defined by f of t is equal to t square comma t cube is a one-to-one map, it is not an immersion at the point 0, at time t equal to 0. Okay, all right, that's pretty much it. Let me suggest a few exercises for you. You need to do all these exercises. So here is a list of suggested exercises. Problem number 9.1, 9.2, 9.3, 9.5, 9.8, 11.4, 11.3, and there are two parts of the problem, 11.2, A and B. Try both of them. Okay. All right. Thank you for attending the 7th lecture for the course of differential geometry.